Alright, so obviously this video is on section 5.2. Section 5.2 follows up nicely on 5.1, which is normally the case, right? But if you remember 5.0, I wouldn't exactly say the same about 5.1 following 5.0. 5.0 was on scatter plots and lines of best fit, right? And then we kind of changed gears heading into 5.1. Reminder, 5.1, that change of gears became solving systems of two equations with the graphing method. So 5.2 is going to follow. You'll see how nicely it follows up. We're certainly not changing gears like we did heading into 5.1. Now, this video, we're going to include the bell ringer that we probably have planned for class. So hopefully you have this paperwork with should look like this, at least in the year 2024. This post 5.1 bell ringer will kind of fast track hopefully. And also we'll probably refer to this activity that also kind of precedes 5.2. Like we do this activity as well in between 5.1 and 5.2. So the bell ringer, especially if you have this paperwork, right? Before we get to these questions, I suppose that this is not on your paper. It's not literally on your paper. So remember, when it comes to solving systems of equations by graphing, if you end up with a picture like this, how many solutions is this? This system would have how many solutions? 1. If your two lines end up looking like this, they're parallel to each other, how many solutions would that be to this system? None, no solution. And if it turns out that your two equations graph the exact same line, one over top of the other, how many solutions here? Infinitely many. Okay? So with that little reminder, you might want to pause, especially if you have this paper, or pause as I click to the next page so you can look at it quick before I move the box in. But please feel free to try this on your own before letting the video roll on. Alright, so just trying to give some, debrief the answers here. Turns out that when you graph both of these lines, you get this kind of a picture, which means there are no solutions at all. And then this is going to be nothing because, the only reason for a question B was if there did turn out to be one and only one solution. You're not just going to say, hey, there's one solution. You're going to actually tell me what that solution is. But not here in number 1. Let's see if this happens in number 2. So when you graph both of these lines with slope and y-intercept, you get this picture. Looks like this one is maroon and this one is green. But how many solutions? Should have been 1. And then what is that one solution? Well, it's the ordered pair, x equals and y equals, together, that these two lines share in common, the point that they share in common. So it looks like x is 4 and y is -3. So that should have been that answer. Again, pause the video as needed. Number 3, long story short, do I really have to plot these, points and make these lines? These are blatantly the same equation. They're going to graph the same line. So what does that mean? Infinitely many solutions. And then number 4, graphing both of these Looks like this one is maroon because it's got a y-intercept of 0, right? And obviously a slope of up 2 over 3, slope of 2/3. So then that would make this one the blue line with a y-intercept of 4. And then this is worth mentioning, I suppose, quick. Not for the first time, I hope. But the slope here is 2, which means like you go up 2 over 1. Well, on this graph, I guess you're kind of out of bounds of the grid. But you can kind of, instead of going like up 2, right 1, you can go down 2 and left 1. That's literally the same slope, or essentially the same slope, maybe. And looks like they're going to intersect at one spot, so that's your one answer, and that happens to be -3, -2. In other words, x equals -3 at the same time as y equals -2, and that would solve both equations. Then hopefully, so this is more flashback. I'm pretty sure it's not just random, like it's there's a method to the madness here. Just again, flashback all the way to chapter 3, where we were just kind of solving an equation for x, getting x all by itself. So for this one that I really hope you tried on your own first, you should have got x equals -1. Pause the video and look at that work if you need to. For number 6, what I probably did was added 4x to both sides to kind of get x's only on, in this case, the right side over here, 5x. And then just kept it going to get x all, so then cancel that out. And then, some people panic or, crap the bed here. Or they, I don't know, they just kind of get tripped up by the fact that, like 5x equals 0. What do I do now? You divide both sides by 5, of course, because all you're looking to do is get x by itself. Now, what is 0 divided by 5? Isn't that something you can do? Of course. So again, always remember, because again, I've seen it over the years, how many people just panic or totally choke at the end here. You can get x equals 0. Like that's a thing. You can have a solution of x equals 0. This one again, hopefully you're trying these first. I don't think there's anything I want to say here necessarily. Number 8. It's possible that this was an extra one. Like, see, I don't, at this point in time, at least in the year 2024, you might have to go on the back of your paper to do this last one. So maybe I'll give you a chance to pause the video again, write this one down, and try to solve for x, okay? Alright, let's reveal what we do. So, I mean, look, might be a few specific things to unpack here and shine some spotlight on. At first, I mean, yeah, you see that there's a fraction, but that shouldn't freeze you up too bad. Like, please don't get scared off by using fractions. What are we going to do? We're going to want to get x's only on one side. So here, what I'm going to do is add 2x to both sides. That cancels these out. And then just what do you do with this? How do you do 2 plus 3/4? Because these are like terms, I mean, that are going to combine over here on the left side. Now, you might want to write this as 2 and 3/4 x, kind of a mixed number. Some of you might be thinking, well, 3/4 as a decimal, that's an easy decimal, that's 0.75. So you could write this as 2.75, which I think is what I did. But I don't know, maybe I won't reveal this just yet. But let's carry on like this. I mean, maybe this will work out great, but maybe something to keep in mind as we move forward here before we talk about the next step. Eventually, with our final answer, you're not going to want to estimate and round off decimals. So looking ahead, what? To get x by itself, we're going to be like subtracting 1 over to the other side, and then we're going to be dividing both sides by 2.75. And the thing is, like, is this going to be a nice enough decimal? Is this going to get us an exact decimal for our final answer? In this case, no. So if you go on your calculator and you do 4 divided by 2.75, it looks like kind of a decimal that you might have to round off or something. So, excuse me. A little sip of water there. So let's kind of go back and remember that instead of writing 3/4 plus 2 as 2.75, we could have written it as 11/4, because 2 is like the same as 8/4. So 8/4 plus 3/4, 11/4. And so here, it might be a little bit nicer of a final answer to think of it as 4 divided by 11/4, which, hey, again, your calculator can maybe even help you out with that. But dividing by a fraction, 4 divided by this fraction, it's the same as multiplying by its reciprocal. So I think the bestest final answer here, whether you use a calculator a lot or a calculator not at all, you should end up with 16 over 11. 16 elevenths, okay? Now, this other activity, before I look into the notes, okay, if you have this at home and if you have a ruler at home, you should do this handout really quick first. But looking ahead at the notes, the official 5.2 notes handout, we saw recall. In 5.1, we saw that if we wanted to discuss a linear system and what the situation is with the solutions, like, solve it, we would need to use the what method? We would need to do what? We need to use the graphing method, just like we did in the bell ringer. So that's the method that we did in 5.1. But can you think of any drawbacks or disadvantages to this method? I mean, hey, it's a great method. Graphing the lines and seeing where they cross each other, what solution they share in common, where they intersect, if they intersect at all. Because by graphing, you might end up noticing that there's no solutions whatsoever, or that there's infinitely many solutions. But this method's good, but guess what? There's some drawbacks and disadvantages. Can you think of any? Well, if you did this activity correctly, this one's good to go for graphing, okay? That's ready to be graphed. It's in mx plus b form. But this one, I did all this work here to put it into slope-intercept form. And so now I'm going to graph this one, and then look what happens. When even if you're using a ruler, you graph this pink line, and then you graph the purple line. Where are these guys crossing? I guarantee you'll be maybe close, but you'll be wrong. Because look at this. It's pretty much impossible to tell with just like the human eye. You could guesstimate for sure. It looks like 1 point something. Like you might even think it's 1.5. For the x value, it's not. And then is it 1? Is it 1 point something? Turns out that the actual answers are 55/38 and y, for x, and then y equals 43/38. And like these are the approximations just to 3 places, but these are approximations. So these are the exact answers. So it's like, how are you supposed to tell that just with the graphing method? Well, you can't. Like that's kind of, here we go. That's one of the drawbacks. That's one of the weaknesses with the graphing method, for solving a system. Can you think of like another kind of situation where like you wouldn't be able to tell where the lines cross at? Well, what if the lines are set to cross like really far away from the origin, like way out of bounds, like on your grid or on your paper? Like you wouldn't be able to tell, like what if you graph these 2 lines and they're not going to intersect each other until the point 120 comma negative 280. You know what I mean? Like how would you know? Like you don't have a paper big enough. So that's another one. And so there's got to be a better way. There's got to be just a straight up algebraic way, which just involves working the equations and not going to a graph. Okay, again, even though the graphing method will actually probably be just fine. Pretty much every example problem you have to do in high school. But as long as you have a grid or something to use. But let's use way more reliable methods that you're going to, quite frankly, just have to be aware of. Okay. So this is the substitution method. Alright, sorry if you notice a little break in the video, like I paused it to answer my cell phone, but here we go. The substitution method. Probably going to involve some substitution at some point. A little foreshadowing there. So if we had to solve this system, okay, and again, we could technically graph these lines and see what's going on with where they intersect. But here's what the substitution method entails. So something I call step 0, which is make sure one of the equations is solved for a variable. And the good news is it really doesn't matter which variable the one equation is solved for. It could be solved for y, or you could have one of your equations solve for x. You got to have like one variable by itself in just one of your equations. Do either of these equations already happen to have x or y by itself? Well, yeah, this one is already solved for y. So that opens the door for step 1, the money step, which is you're going to substitute that equation into the other one. Okay? I mean, because look, think about it. This equation is actually telling you that y equals 2x minus 7. Like y is the same as 2x minus 7. So this y up here in the other equation is replaceable with that entire 2x minus 7. So we're going to substitute this into the y in the other equation because it's an even trade. This equation is telling me that they are the same, and I can replace y up here with 2x minus 7. So that is I guess technically my first written step of work. So now we have 4x plus 3 times 2x minus 7, formerly 3 times y, equals 4. So what do you think I can do with this? Like what was the advantage of replacing the y with what it equals? What's the advantage? What can I do now with this equation? I can now solve for x. This equation now only has one variable in it, the x variable, which means I can solve for x. Remember, solving a system of equations, ultimately all you're looking to do is figure out what does x equal and what does y equal. But when each equation has both x and y in it, you can't really do that the way you can do it here and just get x by itself. So that's step 2. Now we can solve this equation, because you can now, right? And so what would be the first step here? Wouldn't it be, this is probably why I did this in the bell ringer, huh? But what would you do first or next? Wouldn't you want to clear the parentheses? You'd want to distribute the positive 3, and you'd get this, and then you just kind of keep rolling with it and doing whatever you got to do to solve for x, which, combine those together because they're already on the same side, and then just keep on keeping on until you have x equals 2.5. So that's what x actually is going to equal. But why are we not done? What did I say like a minute ago? We not only need to know what x equals, we need to know what y equals. Now the good news is this solution for x, we can totally use this to our advantage. Use that solution. So we're going to, so if x is really 2.25 in disguise, you can now substitute that into one of your equations. I pick this one. It doesn't really matter which one you pick. Try to pick the one you think is going to be easier, So I picked this equation to plug 2.5 in for x. A very good choice, if I do say so myself. And this will basically get you what y equals. So y now equals 2 times 2.5 minus 7. That ends up being negative 2. So the final answer here is 2.5 comma negative 2. In other words, if you were to graph these lines, this one needs solve for y first, but if you were to, do whatever work to graph these lines, guess where they would intersect? At 2.5 comma negative 2. Would you have been able to clearly see that with the graphing method? Maybe. But the substitution method is one of the more reliable, exact methods. No matter how ugly the answer is destined to be, no problem for the substitution method. Let's see here. Quite a lesson we have, huh? Wait, this one, you try. Alright, let me open up something quick. Alright, so this next example, right, what's this over here? Maybe an old example? I don't know, who knows? Ignore that. So, okay, this is my system, and I want to, and as much as you probably could find some graph paper and do this with the graphing method, we're going to do substitution. So what we need is one of the equations solved for one of the variables. We need just one of the equations to say x equals this or y equals that, And it turns out in this one, both of the equations are set equal to y. Like y equals this, but at the same time, y also equals this. So can we go ahead with substitution? Yes. And in this particular, situation where they're both solved for y, you can do something that a lot of teachers call setting the equations equal to each other. Look, think of it. If you go, I could substitute that in for that y, or heck, you could substitute that in for that y. No matter how you approach it, no matter how you see it, aren't you like just setting these equal to each other because they both equal y? It's like saying, well, I think you understand. I was going to use some transitive property type thing, but no need. So now that we have the substitution step over, we can now solve for x, make your moves that you should already be very proficient in, right? End up with x equals 7. But then what do you do now? What do you do after you've solved for x, or after you've solved for your first variable? Because sometimes you solve for y first. Just depends, right? But what do we do now? Don't we have to solve for the other one? So we're going to, now that we know x equals 7, we can plug it into one of these. Which one do you want to plug it into? Because it really doesn't matter. Looks like I'm choosing the first one. So now that we know that x is literally 7, we can figure out what y equals, which is negative 19. This next one, well, man, what are we going to do here, right? Do we have one of the equations already solve for x or y? No. Oh man, so what do we do? Could we like work with one of the equations and kind of move some things around and maybe solve one of the equations for x or for y? Of course we can. But now here is where you're going to want to choose carefully. You're going to want to work smarter, not harder, because, theoretically, you could solve this equation for x. You could. I wouldn't recommend it, because you're going to have to move this term over there, and then what are you going to have to do after that to get x all by itself? Aren't you going to divide both sides by 4? That could get you fractions, which nothing wrong with it. It's not impossible, It's not like you're going to end up with a wrong answer just because you're dealing with some fractions along the way, but I think if you can avoid fractions, let's. Same with going, hey, how about we solve this equation for y? But again, the same thing. Wouldn't you be dividing both sides by 3 and probably ending up with some fractions? No. What would be probably by far the best choice? Getting this equation solved for what? We want to get x by itself or y by itself? I think it's a lot easier to get y by itself. So that's what I did here. Okay. I suppose you could add y over to the other side, and ultimately you get the same answer, but it looks like I moved the 3x over, and then I had to divide both sides by -1. So we end up with this. So now we know that y is literally the same, or essentially the same, as 3x. Now we can do the substitution. Okay? So which equation are we going to plug this in for? Well, here's something you should keep in mind. This came from this equation. Don't ever plug this back into the equation it came from. You got to plug it into the other equation. So now we know that y is basically the same, or is the same value-wise, as 3x. So I can make an even trade. I can replace that y with 3x. That's called substitution. Substituting the 3x in for y. So that was my even trade. And now the door is wide open to solve this equation for x. So 3 times 3x is 9x. What do I do next? Shouldn't I just combine those because they're already on the same side? And then just divide both sides by 13, and you end up with x equals 2. Which, now that you know that x equals 2, you could plug it in to somewhere. Now, I'm hoping I was smart enough to pick this one. It's not one of the original two, but I can plug 2 in for x in this one if I want to. But if you choose either one of these, it's not a big deal. But yep, I was pretty clever. So what does y end up equaling? What's 3 times 2, second graders? 6. So the final answer is 2, 6. Okay? Meaning if you were to graph these two lines, they'd end up intersecting at 2, 6, right? I feel like I want to say right now that you shouldn't get misled by how it's like it seems like we're always solving for x first and then getting y. I already said it a few minutes ago. You could end up solving for y first if you wanted to, and then x. You try this one. So you should pause the video and try this one, please, on your own before unpausing. Last chance, because I'm going to be going over this in 3, 2, 1. Here I go. So the substitution, again, whether you think of it as plugging in that for the other y, or plugging in this for the other y, or just noticing that they're both equal to y, so you can set them equal to each other, this is what you end up with. Okay, if you wrote 4x minus 5 on the left side and 3x minus 7 on the right side, no problemo. But then when you go to solve for x, only solving for x first. What the heck, notes? But that is what x equals, and then you should have went on to, and again, it doesn't matter which one you pick. Looks like I picked the top one. I think here it's kind of a horse apiece which one you pick. I think they're both as easy as the other one, maybe. I don't know. But you should have ended up with y equals negative 13. All right. Now, and then also this one, you should also try this one. So a chance to pause the video before I run through this. Oh, it's got fractions. Is that going to trip you up? Is this your kryptonite? I guess we'll see. Pause the video and try this. But I'm going to go over it in 3, 2, 1. All right. Ooh, just like the bell ringer. Okay, what are we going to do? Well, first, oh my goodness. I did not see this coming, but ooh, something we could have done in the bell ringer instead. Okay, okay, sorry as this is taking like a left turn here, and I have to go off on like a little bit of a side, but here's another weapon you can have in your arsenal here. If you have a fraction or fractions in an equation you're trying to solve, you can clear all the fractions at once by multiplying both sides by, like, you have to pick something that's going to get the job done. You have to like multiply both sides by whatever number is going to clear all the fractions. Now in this one, there's only one fraction that I have to kind of clear. So what did I multiply both sides by to make this fraction not a fraction any longer? Looks like I multiplied both sides by 5, like the whole right side as well as the entire left side. So 5 times 2/5 is just 2. But you have to multiply everything by 5. You have to distribute, and then you have to multiply the entire right side. So that's what I did. That's pretty clever, huh? And so now you're working with something a little more manageable, instead of maybe adding x over and then dealing with like 2/5 plus 1, and kind of like I did in the bell ringer in this video to start the video. Oh well, but this, man, I'm a big fan of this move. Like, I love multiplying both sides by fraction killers. What is this? Oh. Hello. Speak of the devil. This is another way to go, adding x over, and then technically this is 7/5 x, which as a decimal, I believe, is 1.4x. So that, so rather than doing this and just, I don't know, maybe getting like, again, you want to steer away from approximated decimals for your final answer. So this would have ended up as like some kind of fraction, Well, no, actually it would have ended up as, we know, -5, huh? But again, as usual, once you know what one of the, it's always x first. I would like to think that at some point in this notes handout we're going to be solving for y before we solve for x. I have confidence in that. Anyway, so here is where you should probably pause the video and work on this. This is like what we do in class at this point, this in-class assignment where all of these are example problems where you just start off by setting the two equations equal to each other. Alright, so now that you've done the classwork assignment, let's finish up these notes, okay? But to kind of maybe take a few seconds to review so far, remember there's always the graphing method, but even though that's pretty much almost always going to work out just fine, the fact is that a method like substitution is a little more reliable, and all you really need is one of your equations solved for x or y. But when both of your equations are solved for y, I mean, that's a pretty good situation, because you can do the substitution part just setting them equal to each other, but all you really need is one of them solved. In fact, like we've already did, like this example was a little bit advanced, where neither equation was already solved for x or y. So we had to do a little bit of like extra work at the beginning to satisfy step 0, because in this example here, step 0 wasn't satisfied, So this next example, what do you think? Do we already have one of the equations solved for either x or y? Yeah, look, this first equation is solved for x, finally. Finally, we have x equals something. It's going to work the same way. So now that we know that x equals this, okay, like they're interchangeable with each other, x and 2y plus 1, we can substitute 2y plus 1 into the x in the other equation. So remember, that was an even-Steven trade, wasn't it? Because, I mean, doesn't x literally equal 2y plus 1? So now I have this. And so again, why was this good? Because now I can solve this equation for y. I can distribute and then combine these like terms like you've done dozens and dozens and dozens of times. And then just, keep on working the equation to solve for y. And you end up with y equals 5. Okay? So all the, like, after this part, all of these steps should not be confusing to you. They're not new. We've solved equations for x or y or whatever so many times. But so we have y. What else do we need? See, this time knowing y is 5 is going to lead to x. So you can pick which either equation you want, but I'm definitely picking this top one to plug 5 in for y, which will lead to x equals 11. All right? So that means the final answer is 11, 5. All right? Especially if you're thinking of like what point these two lines would intersect at, you know? All right, so I think this is the final example in the notes, right? Final stretch. So once again, I mean, we could theoretically solve both of these equations for y, you know, which means we could then graph them if we had some graph paper, or we could, you know, having them both equal to y is a good thing for the substitution method. We've already pointed that out a couple times. But I think what I'm going to do is only solve one of them for something, you know, because again, for the substitution method, you don't need both equations solved for y or x. You just need one of them. So which equation do you think would be easiest to solve for, like, which variable? One more reminder. If you go, oh, let's solve the top equation for y, you could. Like, there's nothing like wrong with that. But solving this top equation for y, or x for that matter, you're going to end up using fractions when you substitute in. So it looks like I think I'm going to pick this one. And you know what? It's kind of a horse apiece. You could just as easily get x by itself in this equation as you could getting y by itself. So I wonder which one I did. Looks like I got x by itself. But either way, there's so many different correct paths you can take. But here in my notes here, I chose to get x by itself by moving the y to the other side, subtracting it. So now I know that x equals 9 minus y. And you have to plug that into the other equation. Never plug it into the equation it came from. So if x is the same as 9 minus y, I can make a trade. So instead of it saying x, it now says 9 minus y, because they're the same. And again, for like the 5th time or whatever, now I can solve this equation for y, which shouldn't be a problem for you, I hope. Distribute the -2. And then what you should probably do next, you don't have to, but you should probably notice that there's some like terms already on the same side that combine to make -1y. And what would you do next on your quest to get y all by itself? I think I want to get rid of that -18. So I would add 18 to both sides. And then what's the final step here? Because this is not done. What's the last step to solve for y? Remember, technically this says -1 times y. So you could divide both sides by -1, and so that's what y equals. And then what's left to do? Use this answer to solve for x. And again, if you're working the smartest, you can use this equation. It's not one of the original ones, but you can plug 14 in for that y and just end up with x equals 9 minus 14, which is -5. So that's a bunch of examples on the substitution method, and that does it for this video. It was a doozy.